think it's okay. Yeah. Okay. I think I'm okay. Yeah, but I'll take care. All right. So 10 minutes. We lost the 10 minutes. I will do my best to catch up. So this week, I try to introduce the concept called the Bayesian probability and try to apply that probability to the prognostics. My name is Nam-ho Kim. I'm from the University of Florida, and I grew up in Busan when I was young, so this is my hometown. So let's start with the introduction. So physics-based, we learned the data-driven method, but physics-based prognostics estimate the model parameter to the least square method using degradation measurement data. So that's what we did so far. So that in the physics-based prognostics, the parameter estimation is the most important. So it's sometimes called the parameter estimation method. If you use the least square method, then you find there's some minimizing the error between your data and the model, then it will give you a value which is called deterministic. Whereas, since your data is not perfect, your data include the random noise, so your result will be different at the different samples of the data. So it makes more sense to estimate the parameter using probabilistically. So the key point of this week is all about the probability. So what I will do today is we'll talk about what probability that we talk about, how we do it, and a lot of us, including myself, when I was in mechanical engineering students, were not good at the probability. So today's class is all about random variables, probability, what do we interpret the probability. So how to interpret the probabilistic representation of the model parameter. So my model parameter is not a single value, but a distribution. What does that mean? How to interpret? How should I do that one? Okay. So before we do that, did Professor Hichal Kim send you the web link that you can address? So all presentation files are on the web, so you can also download it and look at it. Let's see. So least square method, I believe that most of you, which is called the regression-based method. So I will not go through too much detail about the regression method. I'm focusing on the Bayesian inference. Is the identifying the unknown model parameters and efficiently reduce the epistemic uncertainty. So there are buzzwords here. We need to understand what epistemic uncertainty means, and there are different kinds of uncertainty. So we try to do that. So the concept of a probabilistic parameter estimation starting from Bayes' theorem is Bayes in 1763. So we're talking about 250 years ago ideas, right? So how that idea in 250 years ago now become very popular. So if you are working on developing the AI tools, then inside of tool, a lot of the Bayesian theories are embedded in the inside of tool. So it's very important to fully understand what it does, how it does, what it means. Unfortunately, Bayes' theorem became practical in 1990s due to the rapid growth of the computer. So it's a computer intensive. So that's why the theory was 250 years ago, but actually the implementation is relatively recent. Try to see some point. No. Okay. So how do you guys do the class? Do you have a 50 minutes class and 10 minutes break? Yes. Is that normally you do?
50 minutes plus 10.
Okay. Since I need rest, now it's working. Skip it. The key point of the Bayesian inference is that you need to have a prior distribution. This is a unique idea in the Bayesian method, and then likelihood, and then posterior. So you have a prior something, And you have likelihood and you have a posterior. Posterior is what we want. Okay. Prior, what does the prior mean? It's the prior knowledge. I know about this parameter somehow, even if I don't know exactly, I have some initial idea based on my previous experience, or my professor says so, or some domain expert's opinion says this parameter should not be negative infinity to positive infinity. We don't know exactly, but it's somewhere around. That's the given information. I think the Bayesian method is the only method that utilizes your prior knowledge. Prior knowledge is very important. That's your starting point. If you don't have a prior knowledge, then you can start from negative infinity to the positive infinite possibility, right? It's called a non-prior case. Okay. We'll talk about that later also. Likelihood. Now, in the prior knowledge you exist, now there is some data. One data comes in. Okay? One data comes in. Then now I try to estimate my parameter based on that data. Then you need to ask the question is, how likely that data comes from a value of my parameter. Okay, so that's how we define the name likelihood. And then when we estimate it, what we do, we find the parameter that maximize my likelihood function. So that's basically similar to the minimizing the error in the least square. You are maximizing the likelihood function. Once you multiply the prior with your likelihood, then you become a posterior. What does posterior mean? Is I have a previous knowledge, and I have a data, then I update, then my information is getting better, that is my posterior. So we are try to estimate posterior using samples or data. That's the whole theme of the Bayesian method. All right, getting hard. Computer is not helping me today. And somehow it is frozen, I guess. Okay, all right. So we will try to estimate and update unknown parameters based on measured degradation data using health monitoring system. So your data is coming in from structural health monitoring or different condition monitoring system. Once your data comes in, then you update your parameter based on the data, and you're gradually improving your knowledge about it. That's what I call it uncertainty reduction. So initially, you have a large uncertainty based on your prior distribution. When data comes in, every data reduces your uncertainty. And we will represent the uncertainty in the form of a probability density function called PDF. In epistemic uncertainty. So that's the whole idea that we try to do. First, how we build the prior. Second, when data comes in, then how am I going to build the likelihood? And using that likelihood and prior, and how can I update my posterior distribution? So that's the whole idea that we will do this week. Before we go there, I want to talk about uncertainty first. Aleatory versus epistemic uncertainty. Uncertainty and the random. These are two buzzwords in the statistics, and we need to be very clear about what we mean by randomness versus uncertainty. So aleatory, the first one, we talk about two, right? The first, aleatory uncertainty is random variable. The one that the statistician says the random variables are all in the aleatory uncertainty. This is a variability or type A uncertainty or irreducible uncertainty, meaning you cannot reduce it. There are uncertainties, and you need to deal with it. You need to live with it. Okay, that's that kind of uncertainty. It's inherent randomness. Like wind. If the wind blows, then there's nothing you can do about it. You need to accept that the wind can be strong today or weak tomorrow. You have to deal with it. So you need to design, for example, your system based on the aleatory uncertainty. Then the only thing you can do is you make it conservative, right? When the wind is very strong, you need to build a strong system, stiff system, so that the system can support. Variability in material properties, if you measure the Young's modulus or failure strength of the metal, they are different at different times that you measure it, so that you need to consider that distributions. Or noise in measurement data, or variability in applied load, these are all considered as aleatory uncertainty. So all statistics about the normal, log normal type distributions are customized for this aleatory uncertainty. And then we talk about conservative estimate, right? So if the distribution is such, then you need to have either 3 sigma or 6 sigma conservative value to make sure that your system will not fail under that aleatory uncertainty. So normal distribution. Failure strength, let's say, for example, I take the mean 250 megapascal and then coefficient of variation 10%, which is the ratio between your standard deviation with the mean. Then you can estimate how much standard deviation that I have. And then this is the functional form of your probability density functions. And then we all know that distributions look like this. So that the center is the mean. And then you have a 1 sigma or 2 sigma or 3 sigma covers either 67%, 68%, 95%, and 99%. So these are the common representation of the uncertainty in aleatory. So far the fonts are good. Sooner or later the font will be broken. I will try to fix the problems. But this is the common probability density functions. Okay. Right. So the property-wise, it has to be always a positive non-negative function. And then the probability that we talk about is between the integral of your PDF function between x1 and x2. So the PDF function by itself is not a probability. The area under the curve is a probability. And if you integrate it for the entire domain, then the PDF must be, integral of PDF must be 1. Okay, so the only thing that you need to remember is the bell-shaped distribution is only for the normal, and the probability is the area under the curve. CDF, cumulative distribution function, is the actually integral of your PDF function from negative infinity to a current point x. Okay. So C is the dummy variable, your variable is x. So I use the capital letter F, subscript x, meaning it's a random variable x. The lowercase x is a value of random variable. So it's in the statisticians said it's a realization of the x, but that's this capital X is your random variable, and lowercase x is a value. I mean, this by definition means probability that my random variable x is less than or equal to the small x, which is integral from negative infinity to the current point x of the PDF, which is actually the area to the left of the PDF from negative infinity to the current point x. That's the CDF. If you differentiate CDF with respect to x, then you recover the PDF. So the relationship between PDF and CDF is integral versus the differentiation. Property. Your CDF cannot be negative. Your CDF cannot be greater than 1, because this is a probability. So the maximum of your probability will be 1, and the minimum will be 0. It's a non-negative and a non-decreasing. It's a monotonic function. So your CDF only increases as your x increases. And normally it shows between 0 and 1, and it shows this logistic curve type behavior. CDF at negative infinity will be 0, and the CDF at positive infinity will be 1. And the probability between A to B is the difference between two CDF. Okay, let's go. So this is the integral, CDF is the integral PDF. We already talked about it. How many of you know how to use the MATLAB? What programming language do you guys use? Python. Okay. Any experience on MATLAB? I mean, there are not much difference, right? So probably it's okay. So rand_n is the random number generator. So I generate 500 random numbers out of the normal distribution and store in the variable z. So z is a vector of 1 by 500. And then eCDF is the empirical CDF of z. So basically, it sorted all z in the size of the magnitude, and then increase the probability between 0 and 1. So the blue one is your empirical CDF. And the red one is the standard normal distribution. So that as you can see, how accurate your samples are compared to the true distributions. Normally, we measure the accuracy of your empirical CDF by measuring the maximum distance, vertical distance between your actual empirical CDF with your true CDF. Moment. So this is the integral from negative infinity to positive infinity. Sorry about the font. So moments over a function g. So this E is called expectations. So expectation of a function g, which is a function of the random variable x, is you integrate the g of x by multiplying by PDF of x and integrate it. Then it's called the expectations. And then when the g of x is a simple monomial basis, monomial function, then it's called moments. For example, the first moment is the mean when gx is a monomial linear function of x. So if you integrate x times PDF from entire domain, then it becomes mean of the x. So that's called the mean. And the second moment is when the square of the x, right? But when you take a square, you take actually the central moment, meaning the x minus mu of x. In the square there, you x minus mu x square, and you PDF integrate, then it's called the variance, S of x squared. S of x is called a standard deviation, and S of x squared is called the variance. And there are some formulas that you have it. And the square root of the variance is called the standard deviation. So these are pretty much basic concept in statistics. Coefficient of variation, the ratio between standard deviation over mean. And the third moment is called the skewness. Skewness conceptually is a third order central moment, but the way that we define it is when the PDF is skewed to the right or skewed to the left. It's a little bit of an opposite of your common notion that it's skewed to the right is called negative skew, and skewed to the left is called positive skew. And then skewness coefficient is the scale of that skewness with respect to cubic of standard deviation. Median is the value of x when CDF equal to 0.5. And the mode is the value of x corresponding to the peak value of the PDF. So if you talk about the normal distribution, this one, this is a peak, so that's a mode, right? And then if you actually plot the PDF, that point, when you actually plot the CDF, that peak point is the probability 0.5. So in the normal distribution, your mean, your mode, and your median are all the same. But when it comes to the non-symmetric distributions, and this is a mode, right? And your mean will be somewhere here, and your median will be somewhere other places. So they may not be the same when your distribution is not symmetric. There are fourth order moment is called the kurtosis. I will not talk about here. So there are some way to define the moments. Why do we need the moments? Let's say you have a experimental data comes in. You don't know the distribution. Then you need to somehow estimate what distribution this data comes from. Then now you compare whether this mean is the same of the distribution, and standard deviation is the same, and skewness and kurtosis are the same. If four moments are the same, then it's highly likely the samples or data may come from that particular distribution, right? So this we call it statistical tolerancing, meaning unfortunately in the school we have a distribution, normal, log normal, and we generate the samples. In the practice, it's opposite. You have a sample, and then you need to infer, estimate what distribution it comes from, and what are the parameters of the distribution. So these moments are important to compare, both the finding the source of the distribution and how to estimate them. So these are aleatoric uncertainty, and I believe many of you already know about it. So I will not go through too much. I went through very fast, right? So I understand it because I want to cover more material. But the focus on the first class that I want to estimate time is the epistemic uncertainty. What is epistemic uncertainty? Let's say the world over there, right, made out of concrete, let's say, then it must have some strength, right? Strength. It has a strength, a value of strength, Young's modulus or various strengths. Do I know it?
No.
I don't know it. Is it random? No. It must have some value, one value, but as far as I'm concerned, I don't know. Uncertain. Right? Uncertain. That uncertainty is called epistemic uncertainty. It is not random, it has a value, simply it is not known to me, which in the technical jargon is called lack of knowledge. I don't know. A lot of your model, your system, has some parameter, right? Parameter. But simply, I don't know that particular value of the parameter. So that's the epistemic uncertainty. Let's think about different way. I did not build the wall yet. Right? I did not build the wall. I plan to build the wall. And someone asks, what's the Young's modulus of that wall? Or what's the stiffness of that wall? And you say, well, it will be between 350 megapascal to 550 megapascal. What kind of uncertainty is that? Is it aleatory or epistemic? Think about it. I did not have a wall yet. I will build in the future, right? But depending on who build it, the Young's modulus or stiffness of the wall will be different, right? If it's built on the summer, if it's built on the winter, it will be different, right? Aleatory. It is aleatory.
Because it doesn't exist and it doesn't have an exact value.
It will be any value in the future.
Yes.
So it's aleatory. But once you build it, it becomes
Epistemic
epistemic
uncertainty.
uncertainty, right? So that's the dilemma. Somehow they go back and forth. It was aleatory, but once you build it, it becomes epistemic. Right? All right. State of knowledge, subjective uncertainty, type B uncertainty, reducible uncertainty, lack of knowledge. So the key word here is reducible uncertainty. This is uncertainty that I can do something with it. The previous aleatory uncertainty, unless you control the environment, you cannot control the wind. Wind can blow whatever they like it, right? So that's something that you need to live with it. But this one is something I can do it. And I hope the data can do something. Data is the only realization of the reality that you know about the uncertain situations. So epistemic uncertainty can be reduced through better understanding of physics. I have a better model, more accurate, more detailed, more high fidelity simulation, or collecting more relevant data. Different methods are used to represent epistemic uncertainty. So we have a probability theory, non-probabilistic or imprecise probability, fuzzy set, evidence theory. There are many different kinds of methods to represent the epistemic uncertainty. We need to understand what it means, how they do. But I highlight it, so we will use the probability theory. Probability theory means the aleatory distribution that we talked about before, like normal distribution. I will use that one to represent my epistemic uncertainty. So meaning I will make you confused, because if I draw one PDF, you have no idea whether it will be aleatory or epistemic, right? So that's what we're getting at there. But we will make sure that we understand the difference between the two. Interval analysis. Interval analysis means the knowledge that I have about that variable is between lower bound and upper bound. In between, I have no idea. So even if I use this distribution called the uniform distribution, is it the particular uncertainty will be uniform? Meaning every time when I sample it, they will have some uniform distribution? No, because it's not epistemic uncertainty. It's not aleatory uncertainty, right? So what does this uniform distribution mean? To represent, uniform distribution is very simple between lower bound and upper bound, but what it means is more important, right? So let's, for the moment, I will talk about that later, but for the moment, if I have a lower and upper bound, and then you go through the simulation model, you have output, right? So the relationship between input and output is monotonic or linear. Then it's much easier because then now you collect all the lower bound, you run the simulation, that's the minimum value of the output, and then you run the simulation with the all maximum value, you run the simulation, that will be maximum value. But unfortunately, the minimum of input does not mean the minimum of the output. So if I understand what's the lower bound and upper bound of your input, when your system is a nonlinear system, how do I know what's the minimum and maximum of my output, unless they are monotonic relationship? Well, rule of thumb, you dissect it, many small intervals, run the many simulations, and you find the minimum and maximum. If your resolution is good enough, then you are lucky enough that you will find the minimum, but you can approximate some minimum, right? If there is only one random variable. Now if there is two random variables, how would you do? Grid over the one variable, grid over another variable, you run the simulation of n squared to find the minimum maximum. Three variables, then you need the n power 3 types number of simulations to find it. So this is an expensive process to figure it out what's the minimum or maximum of output when you only have intervals. Probability-based method says, well, I represent epistemic uncertainty as a probability distribution. Then you need to ask a question. What is the meaning of normal distribution in epistemic uncertainty? The normal distribution, right, of epistemic variable. In random variable, aleatory uncertainty, it makes sense if I have more, if I generate the sample, then do you agree there will be more sample here and less sample there? Right? So that's the idea of aleatory uncertainty. What is the normal distribution for the epistemic uncertainty? It's I call it, this is a shape of my knowledge. Shape of my, your knowledge has a shape. Okay, your knowledge has a shape. So what this shape means, I have no preference between lower and upper bound. My knowledge of that variable is all the same. In between, I know it will not happen beyond the maximum, it will not happen below the minimum, but in between, I have a zero knowledge. They're all same. Whereas normal, I don't know exact value, but it's more likely around here. Make sense? So this is significantly different now. Previously, I have a zero preference, versus now, it's I know something that it will happen more likely here, less likely far away. That's the likelihood. That's the likelihood, right? And then for the same normal distribution, some distribution will have a very wide, whereas some distribution will have a very narrow, right? That means the level of your knowledge is much different. If it's wide, then the way that I understand is pretty much uniform. Whereas very narrow means I have a pretty good idea what will happen on the region. So that's the, now in the epistemic uncertainty in the probability-based method is basically the shape of the knowledge. Then if I want to estimate something, then I think this is a good figure says, when I use the 5 samples, you try to estimate the distribution of some failure strength of the material, and you only have 5 samples. Then you can take a mean and standard deviation of 5, right? But that 5 will give you the distribution of my epistemic uncertainty following the blue curve, meaning it's relatively wide. But if I have 30 samples or 30 samples, then do you believe that the mean over 30 samples will be more accurate than mean over 5 samples?
Yes.
That's the shape of the knowledge. This is how much I understand it. If I have infinitely many samples, population is called a population, right? It's all possible situation considered, then this one will be a vertical line. Means now at that point, your knowledge is deterministic. I know exactly what's the mean of the population. Like in the election time, if we ask entire population, who do you want to vote? Let's say, hypothetically, then they will say, I will vote the candidate A, B, or C, right? That will be the outcome of the election day. So there is no uncertainty. You know exactly who will be elected for the next president. But if you only ask, 1,000 or 2,000 people, right? So that will represent somehow the population, but it's different from population. It's only sample. Then you are associated with uncertainty. So that's why in the election poll, they always say candidate A has a 45%, candidate B has a 37%. But by the end of their announcement, it says these values are plus minus what? Confidence interval, right? Plus minus 3% of the confidence interval. That depends on the number of samples they use. So that's how we will represent uncertainty. How at least I want to represent uncertainty. Probability-based method. A lot of people have a lot of people don't like this idea because it's not random. We are estimating a constant value, a value, right? But this is not the randomness. This is the shape of my knowledge. Evidence theory, Dempster-Shepard evidence theory basically says if your knowledge is discrete, but it's interval-wise, so I know the probability that value will be, this interval will be 10%, 20%, here 20%, here 20%, and also they can overlap it, another 20%. So let's assume that you have this type of a discrete knowledge, then you can build more like a CDF, right? CDF is supposed to be a continuous function, but instead you have a stepwise interval function of lower bound, plausibility, and upper bound, I forgot what it was, basic probability assignment. So that the CPF and the CBF. CPF, cumulative plausibility, and this CBF is a cumulative belief functions. So these are the way that the Dempster-Shepard algorithm represented the uncertainty. So this is a very in-depth theory on the evidence theory, but since we are not handling evidence theory in much detail, so I will just forward that for you to read and then search for the Wikipedia if you are more interested to study, so I will skip those. Another example of the evidence theory for different probability assignment. So here is the combined slide for everything together. Probability, this is, you can think about the probability of failure, and you generate using the probability functions. Then the black curve is the probability method. I have a single CDF type curve that represents the probability. Whereas the interval analysis, I have lower bound, I have upper bound. In between, I don't have any knowledge. So either upper bound is 0 and 1. Lower bound is 0 and 1. That's the only, as long as the probability is concerned, it can only tell you upper bound and lower bound. So this is below this point, 0. Above this point, 1. In between, I don't have any right here. Right? So that's the range of your error is from 0 to 1. Evidence theory, in my perspective, is similar to the interval analysis, but it's a sub-interval analysis, right? So you have a probability range in each interval, given in different ways, depending on how much information that is available to you. So this is the slide that I want to emphasize the most here. They compare aleatory uncertainty versus the epistemic uncertainty. A large uncertainty means that samples are widely distributed. There is nothing wrong about wide distribution. It's just the representation of how the randomness comes. No uncertainty means the value or function is deterministic. Epistemic uncertainty, I want you to look at the figure on the left. So if I don't know about the variable, then I will have a large uncertainty. And if I have a perfect idea, then it will become a sharp Dirac delta type function. And if I have a better understanding, then it has less uncertainty. So that's the way that we represent epistemic uncertainty using the probability theory. And I'm emphasizing this is not the universal viewpoint of the problem. This is my perspective, and I interpret the PDF as my shape of the knowledge. Then what I will do is, let's say I have large uncertainty initially. That's my prior. Okay, based on my experience, based on the expert opinion, based on the domain knowledge, this is what I have. And now I have some experimental data comes in, either from the monitoring in the prognostics or some other measurement that you can do it. Then based on data, I can reduce this uncertainty from here to there. Meaning now I understand the problem much better, right? So that's what I will do. The question is, I start from here. If I perform the experiment, where do you think that you get the data? Data could be, I may wish the data could be here, right? That's the hope that we have it, but data is not actually perfect. Data also have its own aleatory uncertainty, randomness. Data could be everywhere. Okay? So how can I get the collective knowledge of the data so that I can improve my understanding of the parameter? That's the key point. Large uncertainty means the information related to parameter or quantity is ambiguous, abstract, unclear. The shape of a PDF is the shape of information or knowledge of the parameter. No uncertainty means the information is fully known, and there is no need to improve any knowledge regarding the parameter. So that's what we will do. So prognostics in the physics-based prognostics means we have a model form. But the model parameters are uncertain, so we are trying to estimate that uncertainty. So the second class will be then how am I going to reduce the uncertainty using the data? That's the second class. But we will focus only on the epistemic uncertainty in the degradation model parameters. Lack of knowledge about the appropriate value of the models. And this epistemic uncertainty is represented by probability density function. For example, if you look at the material handbook, then there is a lower bound, upper bound of the material parameters available. Then you can start from a uniform distribution. The knowledge is only lower bound and upper bound. That's your prior. And then particular batch of the material may have a narrow range of the distribution. Okay. So if you make the metal steel in POSCO, has one group of the process. If you make the same metal in US, the distribution could be quite different. So that if you make the your measurement is on the same batch, the uncertainty will be much narrower than the other cases. And eventually, we want to reduce the epistemic uncertainty using Bayesian inference. I use the word inference because it infers something. My data infer the parameter in some way. So it's called Bayesian inference when measurement data on degradation are available. So that's what we will do. All right. Okay. So okay, welcome back. As I said, I like the very famous lectures in Harvard, Statistics 101, and he said the condition is the heart of the probability. So it's very important to understand the conditions. And the Bayesian idea, Bayesian concept, Bayesian probability is nothing but the conditional probability. Under given condition, what does my probability look like? That's the question that we keep asking. The condition is your data. Okay? So for the given data, what does my probability look like? So So that question that eventually we are going there, and that's based on the conditions. But before we go there, we talk about some set theory. So I have a 3 car depots, and then check what the condition of the car. All 3 cars in the depots are good condition. All 3 are bad. So there are different combinations that you can come up with, right? So these are basically all possible cases. Good, good, bad, bad, good, bad, good, good. These are the cases. And you can collect some set. How many cases that you have 2 cars are good, or how many cases that the 1 car is good. So these are some possible combinations that you can make it. So set is the event with no sample point is an impossible event or null. So complement is that I use the E is event. That's the event E means 2 cars are good condition. So that's the event E. Then E bar complement is either 1 car is good condition, no car is good condition, or all cars are good condition. These are is complement. Okay. The union, intersection, and the complement of x equal to 2. 2 cars are in good condition is the union of no cars good, 1 car good, all cars good. So these are common sense that you do. Venn diagram.
Yes.
Not first, right?
Yeah.
So if you have a high school degree, then probably you heard about it. So we go quickly. So this is your event 1, event 2, and intersection, and this is your complement. So I use notation P of event 1, the probability of having event 1. If 2 events, E1 and E2, are completely separate, it's called mutually exclusive. If E1 happen, then E2 will not happen. If E2 happen, it will not happen. But there are cases that both E1 and E2 may not happen also, right? So that the particular case, either E1 or E2 has to occur. It's called collectively exhaustive. So there is no other case but E1 and E2. Probability. So PE, an event, is always greater than or equal to 0. Probability, non-negative. Probability of a certain event, it always happens no matter what, it's 1. Mutually exclusive, what it means is union is the sum of individual probability. That's the what it is. And the exclusive, the complement, probability of complement is 1 minus probability of event by itself. So meaning, if I add a probability of event and the probability of its complement, it would always 1. And this is the key point. The union of event 1 and 2 is individual probability minus intersections, right? If you have a 3, then you have a more complicated, but eventually I want to only cover area only once, not twice. So I have a simple example. Numbers in Venn diagram represent the frequencies that each event occurs. So that here, event A will occur 16 times, but out of which 11 times are only A alone, 5 times both A and B again occur together. And this is the 15 times there is no A or no B cases. So probability of A, the total events of entire sample space is 48 if you add all numbers, and then the event A is 11 plus 5, so 16 over 48. Event B is 22, right? So 22 over 48, and then intersection is 5, so 5 over 48. Union, you can add probability of A, you can add probability of B, subtract by probability of intersection, or you can count how many altogether, and then you can calculate it, right? So that's the common things that you do. Conditional probability. So let's go a little bit slowly. Key information is how to calculate a intersection of this one. From the law of multiplication of probability. Okay. So the probability that both A and B will occur, that's the definition of intersection, is equal to the probability that A will occur multiplied by the conditional probability that B will occur given that A has occurred. It's so complicated, right? So let's go slowly. So I use this notation, probability B vertical bar A. So what this notation means is A occurred. Then what's the probability B will occur? Okay. If I change it, then it's opposite meaning, but that's what it is. So in the equation wise, this is when A occur under condition, this is condition, okay? Condition when A occur, what's the probability that B will occur? Is over here, A occurred, that's 16, out of which, what's the probability of B occur? 5. That's how we want to count it, right? So then now it's a probability of A intersection B 5 divided by probability of A. Make sense? Make sense? That's a Bayesian theory. That's a Bayesian theory. Now, equation-wise, that's it. How you interpret it, that's different. And how we change it is we change this probability into, we're not interested in probability, we are interested in the PDF, right? So how can I convert it to the PDF? To understand what is my B, what is my A, that's all about this week. So it's not complicated, right? It's not complicated, so don't worry about it. All you need is to completely understand what this means, what this condition means. So what is it? My goal is I want to calculate A intersection B, right? To calculate this one, I have a PA, probability of A occurs, and the probability of B occurs given A. This one says A has to occur, and under which, what's the probability of B occur? That's nothing but the intersection of both A and B occurs. Change the order, then this is B occurs, and then A occur given the condition of B, then that's the same. So both of them are same, right? So then now we can make the equality between these two. A is your experiment. B is your model parameter. So if I have data, then I want to update my parameter. So that's where we try to get eventually. But let's stay on this one for the moment before we actually go to the PDF to fully understand what it means. And I try to prove that this method versus this method should be identical. So let's look at the P, B given A. Given A, 16, right? And then B, 5. So it's 0.3125. And now PA is what? We calculated PA previously, right? 0.33, so it's a 0.33, and then conditional probability, then intersection probability will be 0.104. Opposite, second one, PAB. Given B, what is the probability of A? So given B is 22, out of which 5, so it's 5. So the P condition of A given B is 5 over 22, which is 0.227. So now the intersection is probability of B 0.458, and then condition 227, 0.104. So now whether you go this route or that route, they should provide the same probability of intersections. Any question? If, when it says statistically independent, this is not independent, this is a mutually exclusive case, right? Statistically, this can be independent. They can be even if independent means A and B can happen simultaneously as well, right? Because they are not care about each other. So, independent means, let's try to understand it. This is a conditional probability of B given A. but A and B are independent, right? Whether you take a bus or not, I will take my taxi, no matter what. So that's the probability B. So if the conditional probability is the same as your marginal probability, then it's independent. If this is a B, then this is A times PB. If this is A, then this is B times A. So intersection is nothing but product of the probability, right? So when two events are independent, then the intersection is basically you multiply the probability. In this case, there's nothing you can do about it. There's no condition works, right? Whether I have a test or not, my other result will be always the same, meaning even if I have so many tests or so many data, I will not improve my results. That means there's no useful of this one, right? So this independent is not good. We like each other to be dependent on each other. So if you are getting better, then I will take advantage of you. That's a kind of a theme that we have. California problem. Let's look at it. In the California, how you damage the building, the skyscraper, right? Either earthquake or the fire. You can destroy the building by fire or earthquake. Okay? So the probability of having fire is the event F, stands for fire, and earthquake event E. So, but do you agree there is a chance that there is an earthquake coming in, but at the same time there is a fire on the building? It's possible, right? Earthquake and the building can fire at the same time. So now, individual probability is fire is about 0.5%, and earthquake is 5%. I don't want to live in California if my probability of 5% that I die by the earthquake, but let's assume this number. Now, F and E are statistically independent, because the fire and earthquake, nothing related to each other. So that then what's the probability of structural damage to the building, either fire or earthquake? So that's basically, I want to calculate this union, E1 and E2, right? It's E1 plus E2. Since they are independent, you have an intersection. But that intersection is what? Product of the individual, right? So PE1 times PE2. That's the easy problem. Let's look at a similar problem, but a slightly different angle. A bridge can be damaged by foundation failure and superstructure. So in the bridge, the pillar that's going in, it's called the foundation, and then the one that running, the cars running, it's called the superstructure. I think the statement was not clear, but this or is the key point. So the bridge can be damaged by failure in the foundation F. That's probability 0.05. And or, it's not and, or in the superstructure. So the failure by superstructure, your foundation is okay, and then your superstructure fails. We're not talking about your pillar is bad and your superstructure is bad, they collapse together. No, it's not the case. If the entire bridge will be failed if your foundation fails. If the superstructure is safe or not, doesn't matter. If your foundation fails, then superstructure cannot stay alone, right? So it will collapse it. That's the 0.05. And if your foundation is okay, but your superstructure got bad, the failure is 1%. It's not PF is 0.05, PS is 0.01. It's different. Read it carefully. Foundation failure, PF 0.05, true. What is the second 0.01? What is the 0.01? What probability is that? When foundation is okay, but the superstructure fail. It's a condition. Again, it's a condition, okay? Your foundation is okay, but your superstructure fail. Also, if there is no foundation failure, then the probability that the superstructure will also suffer from damage is 50%. So that's the conditional probability is given. And I want to calculate the union. What are the total probability that it will fail? Okay. And what if the both F and S are, right now it's dependent, but what if they are independent? What's the probability they will go through? So let's calculate this one more carefully by drawing the Venn diagram. The first one, your foundation failure is 0.05. So this blue one, 0.05. Question of how we calculate the superstructure failure is now it's mutually exclusive, right? Mutually exclusive. So F and F bar is mutually exclusive. Do you agree? F and the non-F. That's entire sample space. Okay. So F intersection with S plus F bar intersection S is total probability of S. Does that make sense?
Yes.
Because there is no other cases, right? There's no other cases. So now then, this one use the conditional probability, and this one we take the same. Because this one is given as the 0.01. It's given the problem statement. Here probability of your foundation 0.05, and the conditional probability is 50%. That's 50%. So the total probability of your superstructure failure is 0.035. Now then, union, individual minus intersection. Now the individual minus, when they are dependent, then you use the conditional probability to calculate it. So this is a 50%, and then this 0.05, so your union is 0.06. But if I assume that the both of them are independent, then the intersection is simply product, right? Product. And it actually shows the 0.09.9. So it's slightly lower than the what actually it should be by assuming independent. The take-home lesson here is independent assumption is always underestimate of your probability of failure. So that means it's dangerous. We should calculate more accurately than what it is. Let's take more on the mechanical engineering type example. There are two methods. Okay? So the event A is the number of failed blades in the turbine engine. There are many blades, and how many of them failed by each inspection is event A. And event B is the inspection interval. So the B is inspection time is more than 1.5 hours. And then B bar, the complement is fails before 1.5 hours. So I have event A is inspection time based on 1.5 above or below, and then the event A is a failed or not failed. So this table says if the inspection time is greater than, no, less than, inspection time is the hours of use is less than 1.5, then there are 20 blades are failed and 260 are not failed, total is 280. If inspection hour is greater than 1.5, meaning it used more time, then the number of failed blades are 46, unfailed is 194, total is 240. Okay. So the question is, how many blade fails? Total, 66 out of 520, that's 0.1269. No failure, so you add this column, 454 divided by total, so it's 0.87. So that's the simple case. Inspection within 1.5 hours, so this is this case, right? Less than 5. That's the out of total is 280 were inspected out of the 520, so that's your probability. And inspection after 1.5 hours is 0.46. So that's nothing much new. Intersection of A and B. This one out of 520 is different from PA 0.12, PB 0.53 is 0.0683. So if I calculate intersection of A and B using the table versus if I multiply, individual probability are different, meaning A and B are dependent, right? Dependent. So now let's say how we calculate the correctly, not just looking at this value, how we calculate the intersection of A and B using conditions. This is a formula, this is a formula. Either you start with a probability of B and the probability of A given B, or probability of A, probability of B given A. What does this mean? A given B. Probability of A, right? A given B. No, we need to look at this one, right? B is given, and what is the probability of A? So out of the 280, 20. This one is probability of B given A. So A is given, and then probability of B, 20. So 20 divided by 66. Then now let's calculate the intersection. Either both formula using individual probability PA 0.12 and PB 0.53. So if I use this one, 0.53, condition of A given B, 0.3 or 385. If I use this one, PA 0.1269, and the condition is 0.303, so it's the same. Okay, so that's how the conditional probability is used to calculate the intersection probability. Where do I use it? Let's think about this way. This is before and after test. Proof test. Proof test is what? Proof test. Let's say you have a specimen, and then let's say we tested 100 of them. So now I have a distribution of failure strength. Okay, so some of them failed by 200, some of them failed by 500. And most of them failed at 350. So I have so many samples, and I test it, and then I make the PDF of my failure strength. You can make it, right? That's just collecting samples and making the histogram and plot the PDF. Probability of the strength. This is not CDF that we talk about. This is opposite, 1 minus CDF that we talk about. Meaning, what is the probability that my specimen the failure strength of my specimen is greater than 200? 1. Because most of them are greater than 200, right? This is 1. And what is the probability of strength that my specimen go beyond 500? 0, because all of them fail. So this is a 1 minus CDF. That's what it is. So this is based on my base knowledge of the probability of strength, and this is my PDF. I generated from MATLAB 1 minus CDF, mean 350 and standard deviation 50. So there's no magic here, just simply plot it based on result. Then now I have one specimen. One specimen, I don't know what failure strength is it, 101. 101st specimen, and I test it. You can increase the load, right? You can increase the load, and then it shows, proof test is the particular specimen shows that the strength is 350. I increased the stress by 350 megapascal, and it did not fail. It did not fail. And I stopped the test. So failure strength is you test it until it fails, right? Once it failed, then specimen is gone. You cannot use it. But actually, when I installed a shaft, then I applied the load, and the stress increased until 350, and then there's no failure there. Elastic, right? And I stopped the test. So do I know the failure strength of that specimen? No, because I did not test it, right? That's the dilemma. If I want to know the failure strength, then I need to fail it. I need to fail it, right? Then I cannot use it anymore. So I have to test it below the failure strength, and then I can certify to use it. So that's the proof test. It shows 350. But it's not actual data of failure strength. It is data says it is safe until 350. That's the information that you have. And the question is, how that information can play the role of improving my knowledge. Improving what? Reducing the uncertainty, right? So that without this proof test, your uncertainty will be this distribution. Because that's based on 100 previous samples, so that's the failure strength. But this particular specimen, if I have it, then what will happen? Condition. So this is a strength, random variable. Strength is random, I don't know. 350. That's a condition that I have. The specimen that I tested, it was safe until 350. Then what's the probability of my specimen? The strength is greater than S. So S is your axis. Okay? It has a 350 safe, right? So if I say that S, the lowercase s is 200, probability will be 100%. But it's proved that it is safe until 350, the probability is 1. If I apply the 300, s equal to 300, my probability will be 1. Right? It's 1. Because I already tested 350, it did not fail. I'm not talking about aleatory uncertainty. This is aleatory uncertainty, right? This is aleatory, general specimen, random specimen. But this particular specimen will have one failure strength, which I don't know, but I know it's safe until 350. Meaning, my probability of strength up to 350 will be 1. Make sense? And then beyond 350, I don't know. That's what it is. Right? So now, then let's calculate it. So this is the condition is my strength is greater than S star 350. And what is my probability of strength greater than S? When S is less than 350, probability will be 1. And S is greater than 350, I use this formula, says intersection. There's two events. The one event is the strength is greater than S, and then the other event is the strength is greater than 350 divided by the probability of the second case. So when S is less than S star, when S is less than S star, then if you look at this one, this include this one, right? So this is same as this intersection becomes same as this one. So the numerator and denominator to the same. You cancel it out, it becomes 1. You have a S greater than 350 is this much, and then S greater than S is less than 350 is this much, right? So it's inside of your set. 350 is this much, and then when S is less than 350, it's inside. So that the intersection is nothing but this one. Cancel it. When S is greater than S star, S is greater than S star, then this intersection becomes P of S. P of S. So the P of numerator becomes P of S divided by P of S star. Otherwise, it's 1. So it becomes 1, and then this line is actually the ratio between these two probabilities. If I use the PDF is 0 until 350, and then it has sharp peak and then going down. Because the area under this curve must be 1, right? The area on the red curve is 1, the area on the black curve is also 1, because they are all PDF. Okay. But if you look at the level of uncertainty, this is the level of uncertainty original, and this is the level of uncertainty after you have a proof test. Even if you don't have a failure. Okay? Even if you don't have failure. It's kind of the supervised learning in the data-driven, and also semi-supervised learning. So there are some kind of data, any kind of data. It's not actually fully executed labeled data. You can utilize those data for improving your knowledge. Total probability. Any questions so far? So since we are mechanical engineer, I have a beam bending problem. Beam bending. So you have a force applied 1 applied here, and then force F2 applied there. It's kind of random. So there is some normal distribution of force 1 and the normal distribution of force 2 with a different mean and standard deviations. Applied location is also different. L1 for the force 1 and L2 is at the tip, 9 meters. So probability of PF1, PF2, probability of occurring two loads. Then what is D is the failure. The failure. If the beam fails, where do you think it will fail? If the beam fails, where do you think it will fail? Say on the wall. Do you know the bending moment? Have you heard about bending moment? No? Okay. How many of you know what stress is? Stress. Stress. Have you learned stress?
Yes, strain modulus.
Okay. Bending moment? No. Shear force? So what are your background? Okay. Right. So I think it's important to identify yourself. If I say I'm data scientist, then I have to compete with all data scientists outside, right? If I claim myself as a mechanical engineer, then I have to compete with all mechanical engineers. But think about it, when the mechanical engineers started about 300 years ago. So there are, you can imagine how many superstars in mechanical engineering for the last 300 years. If I want to compete with them, it's inclined playground, and I tend to lose, right? And the same, if you want to identify yourself as a data scientist, the same will happen. Then how can I survive? With this competitive world, right? How can you survive? Keyword, as far as I understand, is interface. Interface. Have you heard about multidisciplinary or interdisciplinary? Nowadays, individual discipline are already fully developed. There is nothing you can do much. The only playground that you can play is the interface. And as far as I'm concerned, every problem or all problem is in the interface. When you think about it, I'm getting old, right? So every morning I have some pain. Where? In my joint. Where is the joint? Joint is connection between two parts. Individual parts are fine, my bones are fine, but the interface is the problem. When you operate your machine, always the joint is the problem. I have a John Deere project. They have about 40 this joint of the excavator. They all have joint, right? These joints are worn out. As you are walking outside, the dirt, sand comes in the joint, so that they worn out. So once the joint is worn out, then you cannot work properly, just wiggling every time, right? But then you stop the machine and they degrind it, and they rebuild the joint. That takes about 2 months. So you can operate the machine for 2 months. That kind of joint is about 60 or 80 per machine. Okay, so they asked me, can you make the all joint worn out in the same process, same time? Because one joint at a time, you need to stop the machine every time, right? So if the 40 of them or 60 of them worn out at the same time, then they will not fix it, they will buy a new machine. Anyway, in the computer program, also same. There are many commercial products available, but not one single software can do every job. So what they do, they are all making the connection between them. Trust me, if you get a job, then probably your job, if you are working on the computer programming or software, is all about the making the interface. You have a finite element software, you have a CAD software, you have optimization software, you have a statistical tool. Individually, they are all working fine, but someone needs to make a connection to make your application works. That's the interface. Your strength is in interface. I know you are claiming yourself as the data scientist, perfectly fine, but as I said, you need to have another discipline to connect. So some of you will work on a biomedical area of data science, mechanical manufacturing of data science. These are basically you are making the interface. So it's good to have one specialty of data science. That's fine, perfectly fine, but you need to have the same knowledge on the other discipline. Otherwise, it will not be fly, this one. So what do you want to do at the second? That's the question. When you graduate high school, you go to college, then basically you choose your major, right? So you are pretty much white paper, so it's much easier to inscribe the new discipline on your mind easy. But once you learn one major, learning the other major is really difficult. Because you get used to this one. So the people, human, are reluctant to adapt, modify themselves unless they have to. So once you are good at one thing, it's very difficult to ignore it almost and then try to do a different one. It's quite different. Manufacturing, okay. So I've seen many data scientists says, well, I don't know what you're doing, but give me the data, then I will handle it. That's a really bad attitude. Okay? You need to understand the source, nature, character, the property of the data, then your domain is much bigger than the person who only take them as numbers. So understanding discipline is important. The mechanical engineering is one of the fields that I get used to. Now if you apply the force here, it will break. Where do you think it will break? It will break on the wall. Okay? It's called the moment. You apply force and then multiply by distance. Even if the force is small, distance is long, your effect on the wall will be much higher, right? So that's the both effect of the distance and the magnitude of the force. So this one, smaller than this one, but has a longer arm, right? Which is called the moment arm, longer distance. So this one may be severe effect on the other one. That's what it is. So will it be failed by force 1 probability? Failed by force 2 probability, then what is my failure? I mean, as the boss, I don't care about it failed by force 1 or force 2. I only care about what's the probability of my system will be failed, which is the conditional probability. Failed by force 1, and then probability of force 1, plus failed by force 2, and the probability of force 2. That's the total probability. This one is only work on F1 and F2 are mutually exclusive. If you apply both F1 and F2 simultaneously, it's a different story. Okay, this is only work when F1 and F2 are mutually exclusive, meaning they are not happening together. If you have many different events that is collectively exhaustive, meaning E1, E2, E3, E4, they are all exclusive, but they cover entire sampling space, then this can be applied for multiple events at the same time. They all need a conditional probability multiplied by its marginal probability. You add them together, that will give you a total probability. All right, where we are. So let's calculate the total probability, knowing the F1 and F2 are mutually exclusive. Failure occurs when the bending moment M, bending moment meaning, bending moment is the force times distance. Okay, so force times distance is greater than 235 kilonewton force times distance meter. So unit is the force times distance. PF1 0.7, PF2 0.3. Then let's calculate the total probability, right? So bending moment for given F1 is the force times the distance, and bending moment of F2 is the force times distance. How can I do that? Let's say. So force times distance, right? So 35 times 6 is 210. So 210. For the standard deviation, it's 4 and the distance is 6. So it's 24 square. Because the standard deviation is the product of the standard deviation with the distance. Same for the, this is the F2 times 9, and this is the standard deviation times 9. That's the probability. Then, conditional probability that we calculated is probability that the bending moment is greater than 235. That's failure, right? Given F1. Right? So let's see how we calculate it. M, I subtract by mean 210 divided by standard deviation 24 in both sides. This is M greater than 235. It's a normalization of the statistics. Okay, so this is normal distribution with a mean 210 and a standard deviation 24. And what is the mean of this one? 0. Standard deviation of this one? 1. So I shift my mean to the 0 and then scaled my standard deviation 1. So this one will follow standard normal distribution. And this one, same scale. This is the right-hand side is determines the number 235 by mean divided by standard deviation. This is the number turned out to be 1.075. Then this X star, this one is standard normal variable. So the probability of this one you can find by standard probability table of normal distribution, and that turns out to be 0.141. And the probability of bending moment greater than 235 for given F2 follow the same process is 0.2893. Then total probability that we calculated is, this is a conditional probability that you calculated, and then probability of F1, and then this is a conditional probability of F2, and then times F2. So the actual probability of bending moment fail is about 0.18. That's the how we calculate it. The only condition that this one needs to satisfy is that they are mutually exclusive. Right? F1, F2 will not happen at the same time, and there's no other load involved in the system, then it will fail by that value.